Welcome viewers, in this video we will see the details about series resonance. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic series resonance. An AC circuit comprising of R, L and C is said to be resonance when the applied voltage and the source current are in phase. At resonance, the power factor of the circuit is unity and the circuit acts as a pure resistance. So resonance is nothing but the current and voltage, applied voltage and source current are in phase. So at that resonant frequency, the power factor is unity, the circuit is pure resistive. Resonance in series circuit is referred as series resonance, while the resonance in parallel circuit referred as parallel resonance or anti-resonance. So we have two types, series resonance and parallel resonance based on the circuit connection. Now we'll go for the further details. At resonance, the power factor is being unity, Z equal to R. Only we have Z equal to R. Inductive capacitance, inductive reactance and capacitive reactance are cancelled. Only R is there. So therefore the reactive part of the complex impedance must be 0. Right? So both are equal. That is XL equal to XC. That is XL minus XC equal to 0. Reactive part is 0. Only we have real part R. So at the resonance, the impedance is only resistance, reactive part is 0. XL minus XC equal to 0. That is XL equal to XC. So both are equal, that's why got cancelled. Only we have resistance. So XL can be written as omega into L. XC can be written as 1 divided by omega C. Right? Bring this omega this side and bring this L that side in the denominator. So omega into omega, omega square equal to 1 divided by L into C. So by taking the square root, omega equal to 1 divided by square root of LC. So this is the resonant frequency, omega equal to 1 divided by square root of LC. You will take this equation number 1. Now we'll analyze this equation. By analyzing the equation, we can go for further. Equation 1 indicates that in a series RLC circuit, resonance may be produced by, first one, varying the frequency for a given L and C. So by varying the frequency, we can go further. Next one, varying either L or C or both for a given frequency. Right? So first one is varying the frequency for L and C. Second one, varying the value of L or C or both for a given frequency. So omega naught equal to 1 divided by square root of L into C. That's the equation number 2. Right. Now we'll see what is the omega naught. Omega naught is called a angular resonant frequency in radian per second. Therefore the resonant frequency is F naught. This is the angular resonant frequency. Normal resonant frequency F naught equal to omega naught divided by 2 pi. Actually omega naught equal to 2 pi F naught. So the F naught equal to omega naught divided by 2 pi. Omega naught is 1 divided by square root of LC. So that F naught equal to 1 divided by root 2 pi into square root of L into C. Cycles per second. This is radian per second. Angular frequency radian per second. This is cycle per second. Omega naught is not depends on R at resonant frequency. So inductive reactance equal to capacitive reactance. Both are got cancelled. Both are equal. And omega naught is not depends upon the resistance at the resonant frequency. Now we'll go for the further details. So consider the series circuit. Resistance, inductance, capacitor are connected in series, energized by the sine wave E, and the voltage across resistor is ER, inductor is EL, capacitor is EC. In a series circuit, when the current is in phase with the applied voltage, the circuit is said to be resonance. Then the phase angle is 0 and hence power factor is unity. So this is called a series resonance. Applied voltage and source current should be in phase, then it is called a resonance. So due to that, the power factor is unity and phase angle is 0. The circuit acts as a pure resistance, that is Z equal to R plus J XL minus XC. You take this equation number 4. So that is the impedance of this series circuit. Resistance plus inductance plus capacitive reactance and capacitive reactive inductance and reactive capacitance. But in this the magnitude of Z is nothing but square root of R square plus XL minus XC the whole square. You take this equation number 5. Right. But at resonance, cos pi equal to 1. The power factor is unity. Cos pi also given as R divided by Z, that is equal to 1. That means R equal to Z. Right? R equal to Z means XL minus XC is 0. So R equal to Z means this term is automatically 0. So that XL equal to XC, XL can be written as omega R into L, because this is at resonant frequency. So that omega is written as omega R. Similarly, XC is 1 divided by omega R C. Bring this omega R this side, with here also an omega R available, so become omega R square. Bring this L in the denominator that side, so 1 divided by LC. So while taking the square root, omega R equal to 1 divided by square root of LC. From that we can calculate the resonant frequency Fr equal to omega R divided by 2 pi, so that Fr equal to 1 divided by 2 pi square root of LC. So this is the resonant frequency. This is angular frequency. This is normal frequency. 1 divided by 2 pi square root of LC. Right. Now we'll analyze the Fr value for the further analysis. Fr or F0 is called a resonant frequency. At resonant in a series circuit, the following main effects are to be observed. Right? So first one, XL equal to XC mean Z is minimum and equal to resistance. That is ZR equal to R, where R is the impedance at the resonance. So the first case, both are equal. That is got cancelled. So Z is only resistance. ZR equal to only resistance. This is called a impedance at the resonance. Z is minimum, so the current is maximum. IR equal to E divided by ZR, that is E by R. Right? So due to this, due to the minimum impedance, we got the maximum current. That is E divided by R. The third one is power is maximum, because IR is maximum. So that power at resonance PR is given as IR square into R. That is IR can be written as E square by R square, IR square into R. So R1 R got cancelled. So E square by R. The power is maximum. The maximum power is given as E square by R. The fourth one is EL equal to I into XL, EC equal to I into XC. So at resonance, I equal to IR, which is very large. Therefore, EL and EC also very large. The voltage across the inductor and voltage across the capacitor also very large, because I is large. In RLC circuit at resonance, both E and I are in phase. Hence, in polar form, it can be written as E equal to magnitude of E angle 0 and current I equal to magnitude of I angle 0. So this is the observation from the Fr, resonant frequency. We will go for the further. We will see the Phasor diagram for the 3 different cases. So this is a Phasor diagram for the capacitive circuit. EC is greater than EL. That is, XC is lesser, XC is more. Capacitive reactance is more. Here both are equal. Inductive reactance, capacitive reactance are both. Then it acts as a resistive circuit. If inductive reactance is more, it acts as a inductive circuit. Right? So F is less than F0, XL is less than XC, EC is greater than EL, so act as a capacitive circuit. F equal to F naught, XL equal to XC, EL equal to EC, it acts as a resistive circuit. F is greater than F naught, XL is greater than XC, EL is greater than EC, act as a inductive circuit. So in this both are equal, so we have ER and EI both are in phase. The resistive current, the voltage across the resistor and current are in phase, and this is the voltage across the inductor, voltage across the capacitor. In case of capacitive circuit, this EL and EC, the resultant is lagging. This voltage is lagging, or current is leading. Current is leading, voltage is lagging here. So this is the resultant resultant output voltage. There is a vector sum of EC and ER. In case of inductive, this voltage is leading, that is current is lagging, right? The E is the resultant, that is a vector sum of EL and EC, right? So here resistive circuit, both the ER and EI are in phase. In capacitive circuits, E is leading or current, E is lagging or current is leading. Here current is lagging and E is leading. So these are three different phasor diagram. Now we'll see the resonant curve for the three different cases. In a series RLC circuit, there are three resonant curves can be plotted. Resonant curves are the graph between resonance and frequency. First one is inductive reactance versus frequency, XL versus frequency. Capacitive reactance, XC versus frequency. Total reactance, X equal to XL minus XC versus frequency. Now we'll see the resonant curve. So the three different resonant curves are available. Here XL is more, having the linear variation. X-axis frequency, Y-axis we have reactance, plus X and minus X. So in case of this, got the linear variation, that is F is greater than F naught and X is inductive. In case of inductive, we are getting the linear variation. Second one, F is less than F naught, that is X is reactive, X is capacitive. So we got the rectangular hyperbolic shape, right? Frequency versus reactance, plus S minus X. So we got if X equal to minus 1 divided by omega C. In case of capacitive, this got the rectangular hyperbolic shape. If both are equal and reactance is 0, we got this value. This both the linear as well as the hyperbolic shape, this where it cuts the curve is called F naught, that is omega L equal to 1 divided by omega C. Both are equal and reactance is 0, right? So for a inductive reactance is more, we got the linear variation. If capacitive reactance is more, we got the rectangular hyperbolic shape. If both are equal, we have linear variation as well as the rectangular hyperbolic shape. At this point, both are equal, that is called F naught. This capacitive reactance and inductive reactance are both are equal and it becomes 0, X equal to 0. So in this video we discuss about the series resonance, the different resonance curve, and we got the expression for the resonant frequency. We analyze the resonant frequency for different cases. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.